Today on Macaulay Math, we're doing right triangle trigonometry. Intro. Okay, good day. I'm Professor Macaulay. This is Math 150, Pre-Calculus, Lesson 18 on right triangle trigonometry. Our goals for today. We're going to evaluate trigonometric functions of acute angles. We're going to use the fundamental trigonometric identities. We're going to use a calculator to evaluate trigonometric functions, and then we're going to use trigonometric functions to model and solve problems. This lesson revisits our favorite trigonometric mnemonic device, SOHCAHTOA. It expands it to include cosecant, secant, and cotangent. Additionally, this lesson covers some simple trigonometric identities such as the reciprocal identities, the quotient identities, the Pythagorean identities, which will be used to solve simple trigonometric equations. Let's get started. Okay, so I've got this unit circle here for us to refer back to if we ever need it. Now, you should be learning your unit circle and committing it to memory. We will be having that quiz here very shortly if we haven't had it already. The next slide, though, is some of the identities that you can find on your trig identity cheat sheet. First, the reciprocal identities, and we used this a little bit yesterday to help us solve a couple of the problems. Sine and cosecant are related as reciprocals of each other. Cosine and secant are related to each other by reciprocals, and tangent and cotangent. The quotient identities, tangent is the quotient of sine over cosine, and since cotangent is the reciprocal of tangent, the cotangent quotient identity is cosine over sine. Some Pythagorean identities, sine squared theta plus cosine squared theta equals 1, 1 plus tangent squared theta equals secant squared theta, and 1 plus cotangent squared theta is equal to cosecant squared theta. Anytime you see a problem involving a trig function squared theta or even exponents, you should be thinking Pythagorean identities. Now, other than that, there's not a whole lot of new math that I'm going to add today, but I do want to do a few examples. So let's look at this one. It says, give the exact value of the 6 trigonometric functions of the angle theta shown in the diagram. Now, when they say 6 trigonometric functions, they want us to find the sine of theta, the cosine of theta, the tangent of theta, the cosecant of theta, the secant of theta, and the cotangent of theta. Now, I put these here this way so that I can just take the reciprocal of this column and put it into that column. All right, so we have to go back to your geometry days and remember that the sine of theta, the sine of this angle, represents the ratio of the opposite side to the adjacent side. That's that whole SOHCAHTOA thing that we talked about in the last lesson. So for me to do cosine, I need the adjacent side to theta and the hypotenuse. I don't have that, but it's not a difficult operation for us to see that I have a right triangle. I have one of the legs. I have the hypotenuse. I don't know this third leg, so I can use Pythagorean theorem to find that third leg. So since it's horizontal, we'll call it x, and I'll say that x squared plus 5 squared is equal to 13 squared. Now, the good news for us is we can figure this out, and it is a Pythagorean triple, meaning that it is one of the rare instances where all 3 of these values come out to be whole numbers. So x squared is equal to 13 squared minus 5 squared, and I take the square root of both sides. And again, whenever you're taking the square root, you should consider the plus or minus value, but since we clearly see that this is a distance, it has to be positive. So I'll have x is equal to the square root. Now, 13 squared is 169, 5 squared is 25, and so I get x equals the square root of 144, which turns out to be 12. So I have a 12 here. So when I want to figure out the 6 trigonometric functions of the angle theta shown in the diagram, I am just representing the ratios, and again, the SOHCAHTOA values of sine, cosine, and tangent. So for the sine of theta, if this is theta, that's the ratio of the opposite side to the hypotenuse. So 5 over 13. The cosine of theta is the ratio of the adjacent side to the hypotenuse. So 12 over 13. And then the tangent is the ratio of the opposite side to the adjacent side. So 5 over 12. And then the cosecant, and again, I find these by using the reciprocal identities. The cosecant is 1 over the sine, or the reciprocal of the sine. So all I have to do is flip these ratios and give me the reciprocal of the fractions, which will give me 13 over 5 for cosecant. It'll give me 13 over 12 for secant, and then 12 over 5 for cotangent. And that is all 6 of those values. Next, it says, given the acute angle theta and 1 trig value, find the remaining trig values. So they give me the cotangent of 5. They want me to find the remaining trig values. So let's do it the same way and go the sine of theta, the cosine of theta, the tangent of theta, the cosecant of theta, the secant of theta, and then the cotangent of theta, which we know to be 5. For the sake of argument, since cotangent is a ratio of sides, let's make this a ratio. Let's make it, because it's 5, let's make it 5 over 1. Now, I cannot make a statement about the length of these sides, but I can put in placeholders, all right? I can say that to the opposite side and the adjacent side will have a ratio of 5 to 1. Now, is the side length 5? I don't know. I cannot make that statement. It could be 1 and 5. It could be 2 and 10. It could be 3 and 15, all right? I don't know those length values, but I can put these placeholders in and use them to get the ratio. But just like in the last problem, I am missing a value for the hypotenuse. So I will use Pythagorean theorem to say 1 squared plus 5 squared is equal to the hypotenuse, which we'll call c squared. And so c will equal the square root. Now 5 squared is 25, 1 squared is 1, and so I'll have c equals the square root of 26. Now, 26 only has 4 factors, 1, 2, 13, and 26. None of those are perfect squares, so unfortunately, this problem doesn't come out to have all nice whole number values. Okay, so if I want to do the sine of theta, that is going to give me the opposite side 1 to the hypotenuse square root of 26. So let me scroll down just a little bit here. That will give me 1 over the square root of 26. Now, you are not supposed to have a square root in the denominator of your final answer. So I'm going to multiply this by a funky 1, and that funky 1 will be the square root of 26 over the square root of 26, which will give me 1 times the square root of 26 is the square root of 26, and then square root of 26 times the square root of 26 is just 26. And so I will put that up here and go square root of 26 over 26. Similarly, I would have for the cosine, the adjacent side 5 over the hypotenuse square root of 26. If I use this same process here and multiply by the funky 1, square root of 26 over square root of 26, I'll end up with 5 square root of 26 over 26. And for tangent, since I already know cotangent, I'm just going to do the reciprocal of what they have. I don't have to do any further work. I'm just going to go that this is going to be 1 over 5. And remember, since we're doing our final answer here, we'll just make that into 5. Now, cosecant is the reciprocal of this thing. But if I take the reciprocal of it, I'll put the square root back on the bottom. So I'll have to do more work. All right. So in this case, the cosecant will be the hypotenuse, since it's the reciprocal, over the opposite side. So square root of 26 over 1, the square root of 26 over 1 would just be square root of 26. And then if I do the secant, that would be the hypotenuse over the adjacent side, which is square root of 26 all over 5. And I have given you all of the remaining trig values. All right, next, fill in the table given the acute angle theta. So I have the cosine function and it's 60 degrees. So they want me to find the radians value and the function value. So 60 degrees converts to radians. And again, hopefully you are memorizing your unit circle and you can remember that 60 degrees has a radian measure of pi over 3. And then the function value, the cosine of 60 degrees or the cosine of pi over 3, they're the same, would be the x value at pi over 3, which is a half. That one's pretty easy. Next, it says use trigonometric identities to transform the left side of the equation to the right side of the equation. And we're going to be doing a lot of this in the next couple of lessons. And one powerful tool that you will be regularly using is to convert all terms to sine and cosine. And if we look back up here at those identities, we see that the cosecant is the reciprocal of the sine function, and that works even if it's squared. So if I come down here and I go to my next step, cosecant squared x is the same as 1 over sine squared x times sine squared x equal to 1. And if I multiply that out here, one times sine squared x is sine squared x. Sine squared x times 1 is sine squared x. And anything over itself is just 1, so I get 1 on both sides. I have converted the left side of the equation to the right side of the equation. Okay, last example. It says traveling towards a mountain directly in front of you has an angle of elevation of 3.5 degrees. After traveling 13 miles, the angle of elevation is 9 degrees. How tall is the mountain measuring from its base? So I have a diagram drawn. It is definitely not to scale. But what they're saying is this is 3.5 degrees and this is 9 degrees, and they say that this length right here is 13. I've traveled from here to get 13 miles, and they want us to figure out that value y. Now what I do not know is what this value x is. I do not know what that value is. I have two variables. That means I am going to need two equations to solve for both variables. It's just a system of equations. Now, if I look at it, I have two triangles. I have the first triangle right here that is 9 degrees. It has a right angle. I have x and I have y. And then I have a second triangle right here that has 3.5 degrees, has 13 plus x, and it has 9. Now, in each case, I know the opposite side and I know the adjacent side, and I know the angle theta. So I'm going to set up two tangent expressions, and I am going to say that the tangent of 3.5 is equal to the opposite side y over 13 plus x, and that's a decimal right there. And I'm also going to say that the tangent of 9 is equal to just y over x. Now remember, it says how tall is this mountain? That is this value right here. That's what I'm looking for. I'm solving for y. I would like to cancel out x's. Unfortunately, that is not the easiest way. So I'm actually going to cancel out y's. That means at the end I'm going to need another step. I'm going to have to plug in. That's okay. It's not a big deal. But the reason that that ends up being the case is I can multiply both sides by the denominator and get y by itself. And what that'll look like is I'll have 13 plus x times the tangent of 3.5 is equal to y. And then I'll have x times the tangent of 9 equaling to y. And again, I'm trying to find y. That's my goal. But I have two equations that are equal to y, so I can set them equal to each other. I can say that 13 plus x times the tangent of 3.5 is equal to x times the tangent of 9. All right, so I want to get the x's together, and you can do a couple of different things. I only want to make one calculation at the end. If you want, you can calculate the tangent of 3.5 and just type that in decimals. Remember to change it to degree mode instead of radians mode, which is the default setting. But I'm not going to do that. I want to keep these together. So I'm going to distribute this tangent of 3.5. So I'll have 13 tangent 3.5 plus x tangent 3.5 is equal to x tangent 9. And then I am going to subtract this x tangent 3.5 from both sides. That'll give me 13 tangent 3.5 is equal to x tangent 9 minus x tangent 3.5. Now this, again, I can calculate it. I can put 13 times tangent 3.5 into the calculator. It's done. I still don't know what x is. So here's, I will factor out an x. And so I'll have the 13 tangent 3.5 is equal to x times tangent 9 minus tangent 3.5. I've just factored an x from both terms. And here I will divide by this expression, tangent 9 minus tangent 3.5. And that'll give me x is equal to 13 tangent 3.5 all over tangent 9 minus tangent 3.5. Now I'm going to do that in decimals. So let's go over to decimals. And before we can do anything, since we're working in degrees, I have to come over here to this little wrench. And when I look at the wrench, I need to put it into degree mode, or else I will get the wrong answer. So now I'm going to plug in what I had from that last one. It was 13 tangent 3.5 all divided by the tangent of 9 minus the tangent of 3.5. So x is equal to 8.178 miles. Now, I know that was a lot, but remember, we're not solving for x. That's this distance here. They want to know what y is. The good news is I have two equations that are already done for y. I have x times tangent of 9 is equal to y. And so I'm just going to do that. I'm just going to go x times the tangent of 9 equal to. So when I go back to decimals, I want to use all of these numbers in my final answer to get the best answer possible. So I'm going to go a equals, and then I'm going to go a tangent 9, and that's going to give me 1.295, and in this case 1.295 miles tall. All right, well, that's all I got for today, folks. So The Star Wars fun fact of the day: in original drafts of Star Wars A New Hope, Darth Vader and Anakin Skywalker were two different people, but were eventually combined into the same person in the script of The Empire Strikes Back. Well, that's all I got for today, folks. Have a great day. Goodbye.